Hello everyone and welcome back. My name is Mr. Cobalt, and in this video I'm going to be covering how to write resonance structures. So here I have on the board are two examples of molecules that I will be going over that exhibit resonance. So right now I wrote ahead of time the Lewis dot structure, or at least one of the Lewis dot structures for each of these molecules, and I'll show you how to write the rest of them. So let's start with NO3 minus, our nitrate ion. So you'll notice that here's the Lewis dot structure. Notice that I have square brackets around the Lewis dot structure because it has negative charge. This is the way you do the Lewis dot structure for negative ions. You have a square brackets around the Lewis dot structure with the charge on the outside of the square brackets. So let me make sure that's more pronounced. Negative. So then these are the Lewis dot structures. If I didn't have, if I had a positive charge, or if I had a neutral molecule with no charge, then we wouldn't need the square brackets. But since we have negative charge, we have the square brackets for our Lewis dot structures. All right, so remember what resonance structures are. Resonance structures are structures where the connectivity of the atoms is the same, they're connected in the same way. The only difference is that the electrons are moving. So formal charge should be the same, number of electrons should be the same. So if we've got our true Lewis dot structure, then what we do is we find where could this double bond move to, right? And so one direction that this could move to is you could take two electrons from one of these bonds, and you can move those two electrons here, right? So, or the way it could work is if I move these two electrons, and this is kind of showing the motion of electrons. So these electrons can move here, right, forming a double bond there. But remember, nitrogen is in period 2, so it cannot have an expanded octet. So if I left it like this, I'd have a double bond, and a single bond. That would be 5. That'd be 10 electrons. That would violate the octet rule, and nitrogen can't have an expanded octet. So, so if I'm going to create a double bond here, then the double bond here has to be broken. So then the electrons here are going to be moving back onto that oxygen. So I would draw that as a Lewis dot structure. So in this case, I'd have 2 lone pairs with the nitrogen, and then I'd have, this is the same, and then I'd have my double bond there, and then I have a single bond here with 3 lone pairs like that. So then the only difference is the motion, the movement of the electrons. So I could have done it the other way, where instead this pair of electrons would move, right? So I could move these pair and make a double bond there, and then these would move on to that one, creating another possible resonance structure. So in that case, it would be single, double, like so. And these two, okay, here we go. So then these two oxygens have single bonds and 3 lone pairs. This one would have a double bond and 2 lone pairs. So you can see that the only difference between these Lewis structures is that the double bond is located at different places. So this is how you would draw Lewis dot structures, and you would have double arrows between all of them. representing the fact that there is resonance here. And once again, let me clarify that in reality, this molecule is not having its double bond switching back and forth. It's not like the molecule, this double bond is flipping back and forth between all of these structures. That's not what's going on. I know that the word resonance kind of implies that idea, but that's an unfortunate circumstance of history and our inability to kind of describe it succinctly. So what we really mean is that whatever the molecule is, this molecule, this nitrate ion, whatever it looks like, it's an average of these, right? So what you could do is you could kind of figure out the bond length here and average them by counting the number of resonance structures you have. And then the number of bonds you have as well, right? And what kind. So the total number of bonds you have here in your molecule is 1, 2, and 3, and 4. And all of them have 4 bonds. But then you have 3 different structures. So if you divide the number of bonds by 3, then you get, what is it, 4 thirds. So this gives you 1 and 1/3 bonds. So since these are all equal atoms, so they're all oxygen, the bonds are either going to be double or single bonds between nitrogen and oxygen. So they're all going to be equal bonds. So the average gives them a bond. This is called bond order. Bond order, which is basically saying like what kind of bond you can have, a double, triple, single bond. And so you notice that if we take the average of this, then this tells us that we have about 1 1/3 bonds for each of these. So dividing these or averaging the bonds gives us a bond order of 1 1/3. So each of these would have a bond order of 1 1/3, and we will represent that as this. So the hybrid resonance structure would be this here. So we would draw it like this. And so we would have oxygen, and then with the nitrogen, oxygen, and then you have something like that. So this is the way we would represent the hybrid molecule of our nitrate, with a solid line and a dotted line, meaning that it's between 1 and 2. It's between a single and a double bond. So it's not completely just a single bond. It's not completely just a double bond. It's somewhere in between, and that would be like 1 1/3 bonds. Okay. What about our nitrite ion? So we only have 2 oxygens in this one. And again, the idea is the same. So I can move these electrons here to make a double bond there. And again, nitrogen can only have an octet. So then what's going to happen is that these electrons, that double bond has to become a single bond, right? And so you get the double bond on the other side of your Lewis dot structure. And there's our negative, and we have 2 lone pairs there. Don't forget the lone pair on the nitrogen. And so here's this one. In this case, we have 2 Lewis dot structures that have the same connectivity, but the only difference is where the electrons are. And again, you'll notice with the formal charge, and remember, formal charge is equal to valence electrons minus non-bonding electrons, your lone pairs, minus bonding electrons. So I'm not going to go through how to calculate that except for that there, but I'll write down the formal charges. Again, if you want to know how to calculate that or seek and get practice of that, see my video on assigning formal charge. So we know that this one's going to have a -1 formal charge, this one's going to have a -1, and this one's going to have 0, and this one's going to have a plus formal charge. So nitrogen has a plus, and it's going to be the same for all these. This one's a plus, but this one's a negative, this one's a negative, and this one's 0. And now for this one, this is negative, this is negative, this is positive, and this is 0. I forgot. Oh, there it is. So you'll notice that all of the resonance structures have the exact same total formal charge. And so also the same number of electrons. Here, same thing. Here you have -1, and here you have 0 formal charge, and here you have 0 formal charge. And notice that they follow the bonding pattern. The ones that are 0 formal charge follow the bonding pattern that is typical for that atom. So oxygen has 2 bonds, 2 lone pairs. Nitrogen, 3 bonds, 1 lone pair. So it's 0. This one does not follow the typical bonding pattern. So, but it does have the bonding pattern that has -1. So, but you can calculate that out. So this one has 0. This one has -1, and this one has 0. So again, the only difference between these two is where the electrons are and where that double bond is. The total number of formal charge is the same. What else is it I wanted to talk about? So again, with regard to bonding, right? It's not like this is flipping back and forth between these two. This bond really is not moving back and forth. But what I do want to stress, though, is what this is representing is the delocalization of electrons. That's the key thing here. The electrons really are fluctuating here. The electrons really are moving, but it's not like you have, a double bond at one point, but then you got a single bond, and at another point you got a double bond. It's not happening like that. The electrons are always in flux. The bonding is representing probability maps of finding those electrons. And so when you do an average of this, in this case, you have 2 resonance structures. And then you've got also 1, 2, 3 bonds. So you have 1, 2, 3 bonds that are being averaged. So these two are the same element. So if we count the number of bonds between where this double bond is flipping, so it'd be 3 total bonds, and then you have 2 Lewis structures, 2 resonance structures. So it'd be 3/2, which is 1.5 bonds. So the bond order for this one would be 1.5 bonds. So we could draw the hybrid structure again. So the hybrid structure would be, let's see, like this. Something like that. And so notice again, you have 1 solid line, 1 dotted line. So this is telling us that whatever bonds this has, it's got an average of these two. So in reality, it's not a single bond, it's not a double bond, it's a 1.5 bonds, right? That's the reality. It's a 1.5 bond in the molecule. So it's not flipping back and forth between 1 and 2. It just stays. It's got a bond order. It's got a bond of 1.5, not 1, not 2. It's 1.5. Same thing with these. The bond order is 1 1/3. So that's each of these exactly the same length, exactly the same amount of energy. So they're all the same bond. So 1 1/3 bonds for each of them. 1 1/3 bond. So whatever this molecule is, this is 1 1/3 bond, this is 1 1/3 bond, this is 1